for the presentation. And thank you so much for all of you guys, especially Uniform, to giving me a chance to present my work that I did a little bit a while ago. So the problem is actually related to some biological science, but I will try my best to focus on the reinforcement machine learning thing and more towards the mathematical or the computational sides rather than focusing on the application. But still, I didn't have any other way to eliminate totally the population in the application. So I'm going to talk about an aspect of reinforcement machine learning in scientific research problems. I will start with the introduction, the machine learning and reinforcement machine learning. Then I will give a simple example, and I will come towards the application side, that is in the biological sciences, and there are some results and analysis, and rather than will be conclusion. So the purpose of machine learning is there are two concepts normally that are followed. One is called nativism and the other one is called empiricism. Scientists believe that either we have some knowledge pure, that is called nativism, and we started building on it. Whatever we do, that is actually mostly followed in the machine learning, that we put knowledge inside and start expecting some behavior from the computer. The second one is empiricism. In empiricism, you say that there are only concepts available, but knowledge was not there. So everything you started learning right from zero, and with the passage of time, you understand that when you are doing something wrong, you understand, you learn from there, and you do it right in the next step. So based on these two concepts, I think I can say that supervised and unsupervised learnings are mostly based on the nativism approach, and reinforcement machine learning is mostly based on the empiricism approach. Although we need some, if we have the data, that's great. That's why you can see here that data is provided in supervised and unsupervised machine learning. In reinforcement, we don't need that. We need the concepts. In supervised and unsupervised, we have the features defined or not defined, but in reinforcement, you can extract the features. And also, we have some predictive modeling techniques available in mostly in the mathematical statistics. In supervised and unsupervised learnings, in reinforcement, there is no predefined modeling technique. You have to build your own. You understand the phenomena, and you start writing your mathematical equations, and then you make a strategy, that which strategy is better to tackle this problem. So for the optimization part, in supervised and unsupervised, we actually optimize the behavior that we already have in the data. But in reinforcement, since we don't have data, we can expect some optimal outcome or the possible outcome that is the best in any situation. So I will just explain a little bit more about reinforcement machine learning. So it is also called trial and error approach. You try. If you fail, you change your direction and try something else. If you fail again, you try the third one. And at the same time, you are learning. You are learning the new ways that the previous ways were failed. You don't have to go there. And there are some payoff and cost functions involved. These are the reward functions. And you give either some reward in positive sense or punishment in negative sense. So that is the cost function is right at the end, and on basis on this function, we take the next step. Reinforcement tries and check its reward punishment and decide the next step. Goal is to maximize reward, minimize punishment. The figure is actually self-explanatory that there is something going from agent to environment. Environment is responding back, and agent is performing its operations in the spectral way. This is the only slide where you will find that much English. So just read it once and see what are the keywords coming and why, under what circumstances, which keyword is utilized. So imagine a kid is given with a television remote control to start his favorite TV show, mostly cartoons. First, he, the agent, he will be an agent, will observe and construct his own representation of the environment, that is the state. Then his curiosity will take certain action to press keys on the remote control, that is the action, and observe how would the TV respond, next state. If the TV is not responding, he will dislike it, receiving a negative reward, and will take less action that will lead to such a result, updating the policy, and vice versa. He will repeat the process until he finds a policy that is giving him better response. So actually this one paragraph is, I found it better to explain the reinforcement machine learning in a sense that I'm going to use. So the goal is to maximize your positive reward, so right at the end he will learn that how to switch on his favorite TV show. Next time he can just directly follow the directions that he found the best ones. And I would say the last thing is that is it possible that he finds another TV show? Is there any possibility that one TV show he really likes, but is it possible that there is another TV show going on at the same time on some other station, and he may like it more, but he is not actually approaching that TV show because it might be far away or he doesn't know how to operate, how to go there. So these are all the possibilities that is telling us that reinforcement machine learning is not taking us to the optimum value sometimes. So I actually use this in budding yeast problem, that is the aging problem. Our goal was not to make some infinite life. Our goal was totally that we should make our lives healthier so that we do not get so many diseases in our earlier lifetime. So right at the later stage of life, when our body is already exhausted, at that time, suddenly all the diseases come and we go. We don't have to spend a lot of time in hospitals. That is actually the benefit of the government and the health industry. So, why do we choose yeast? Because yeast has many homologies with humans. They are budding steadily with age, like they get scars. As you can see, bud scars I'm writing in the picture. And they have increase in cell size. Their cell size increases as they are producing more and more cells, and they are easy to manipulate, and they are less expensive, and very useful in food industry as well. So if we are using them, then we can actually not only trying to understand the human aging process, but also we are using the same yeast in the industry as well. So almost they say that 30% of the genetic material in yeast is similar to the genetic material of humans. So that's quite interesting, especially in the aging side. So what happens in yeast? Why is this so easy to use, easy to manipulate? First of all, there are only two processes, growth and division. Secondly, there are only two components. You can divide cell into two components. One is damaged, one is healthy. So the healthy one is performing all the good operations. Damage is just like garbage, collected inside the cell. And as this damage will grow, cell will die. As you can see in the left figure, so there is a cell that has no damage inside. So red spots are damaged, and the rest of the cell is like good. And the green circles are the one that I told you, these bud scars. So as you can see that in the beginning, cell is growing and producing a little bit of damage. In the beginning, the daughters it is producing, they are damage free. As it produces more and more daughters, it starts giving damage to the daughters. So it shows like there is some altruism, there is some selflessness behavior by the mother. That mother is trying to produce healthier daughters, but at some stage of her life, she is unable to retain all the damage. So she has to give a little bit damage to the daughter so that she can produce more daughters. So that's what I'm calling it altruism. And mother yeast shares everything proportionally equal with her daughter except the damage component. And I will call it as damage retention mechanism or in the mother cells. And it is very well proved in the scientific community. So the problem here is that when we increase in damage retention, the mechanism we are making mechanism better, more efficient, the mother life actually decreases. She can produce, she will be able to produce less daughters. When we are decreasing damage retention, then she can produce more daughters, but the life of the daughters will be not that much good because they are getting the garbage inside, and the whole colony will be not that much healthy. From evolutionary standpoint, that's a famous actually phrase that motivated me to work on this side, that these cells are tuned for optimal reproduction success and not for long-term survival. So it means is that they are trying to produce more and more healthy cells rather than surviving for a long period of time by their own. So here I'm explaining a little bit about that how this whole life cycle goes on in the colony wise. So there is a, in the figure on the left side you can see the blue circle inside it written D as daughter and M as mother. So daughter is dividing into two cells, one is becoming mother and the other one is the daughter. Now mother is again dividing and producing one more daughter down, and in the same way the hierarchy goes on, and at the end mother is dying. Right on the bottom left of this figure you can see that there is a cross and circle. So damage is increasing, as you can see the above figure on the top of the figure, that right at the end we have a very mixed the yeast cells population in the colony. Few are healthy, most of them have damage, and some of them have like a lot of damage in them. They are going to die. Our objective is here to minimize the damage, maximize yeast population. They both are like going opposite to each other. If we are minimizing the damage, then the yeast population will be minimized as well. We want to maximize it, then the damage will be increased as well. So second thing is about the optimal reproduction success. That if we are going to find such point, would that be global or local? Where actually, in the evolutionary point of view, where actually the yeast cells, if they are really evolving and they are really going towards some at the optimal place, are they really at the global optimization, or there's a local optimization problem? And the main and like the major thing is that can two yeast cells give the same optimal value if each have a unique strategy of retaining damage? So here I mean is that there are two daughter cells. They are coming from the different strains or different types, different kinds. They have their own damage retention mechanisms. Now, in the long term, why, from the evolutionary point of view, why they are not behaving in the same way? If evolution is driving them towards some optimal side, a global optimal, why they are not becoming the same? And yeah, so if they have some optimal reproduction success, would that be same or not for both of them? So until now, if you guys have any question, that will be like, I can go on, otherwise then the mathematical work will start.
Sorry, how do they quantify the damage? Like visually, or how do you know?
So from the experimental side,
yeah,
from the experimental side, actually there are many techniques they can use. They actually have to see sometimes with the microscope, unfortunately, sometimes manually they have to see. They just take the picture and see the black spots coming inside. So the black spot, they consider that these are the damage. They actually take their length and see that how much damage is happening in the cell. Any question from the biological point of view, or should I go ahead? Okay, so as in the last slide, I was talking about some two yeast strategies. So I built some two yeast strategies, and I named them distance strategy and deviant strategy. I didn't show that why I named them distance and deviant strategy, but I can tell you that there is a reason behind. Distance strategy is that how far it is from the depth, how far mother cell is from the depth. Deviant strategy is that it is just counting the replications, that how much daughters I have already produced and how many more I can produce. So in that sense, I made the distance and deviant strategy. I used the regressive Hill function. That's a quite common and famous function, regressive Hill function. Normally people use it from the curves. Everybody can understand that how it's going to behave. So I am trying to make this function behave like this one. So here you can see that some curves are coming from upside and some curves are going from downside. So my deviant strategy is decreasing the damage quite fastly in the beginning, and then after they stop. While my distance strategy is retaining the damage in the beginning, and then after it drops down quickly, because when it comes to know that I cannot produce more daughters, then it will drop all the retention, and it will start sharing all the damage with the daughter cells. I would just like to repeat one thing again, that our problem was minimize the damage and maximize the population. So on the basis of these two phases, minimize the damage and maximize the population, we are trying to build our strategies. And retention, in the last slide, here we were finding the retention, but this retention was just to make some sort of generalized behavior of retention. For each strategy, how the retention is going to behave. Here we are trying to tell that this retention is actually not only depending on generation, but also depending on the altruism factor. And here we can see that we are making 5 different altruism factors. A equals to 0, 0.25, A equals to 1 means that's a selflessness behavior. And A equals to 0 means that's a selfish behavior. And in between, we can find 3 more. On the bottom x-axis, we have the deviant number, generations. And on the y-axis, we have the retention based on the altruism and the generation number. So you can see that at A equals to 0, that's the blue line. It's right on the bottom, and it's the maximum one, because they can produce more and more population, more and more daughters. At the same time, for the A equals to 1, the green line, you can see that the green line is just dropping down from the top, and it's unable to produce that much daughters when we run the simulation. Now we have to find something in between, there is something or not. So we are trying to build the reinforcement learning model. But before that, there are some prerequisites that we have to follow. And we have to set up our table for the reinforcement. To start the reinforcement, there will be an algorithm. How to find the cost function. For this cost function, we have some theory behind that. We have to build that theory before. First of, when we will be finished with it, then we will find the cost function. When we will finish with the cost function, then we can say that we are talking about the stochastic problem. Yes.
In the previous two slides, you have some formulas.
Yeah.
You come up with them, or they are a result of the previous one?
So I actually, when I started working on this problem was done until this point, on the right hand side. This is a very simple figure that is explaining the damage and the healthy in a single yeast cell. That it is producing daughters and it is fluctuating. That the component is going up and then down because it produced daughter, and then again it is growing and then turning down. So until this level it was done. Then after I had to make my own formulas, understand the behavior of the biological problem, and make the formula accordingly, and set this formula accordingly as well in the same way. And all these formulas as well. We had to these formulas are based on some kind of intuition as well. How you are feeling that cells, this whole process is behaving. In the similar way, you will write the formula, the equation, so that equation shows you some sort of similar behavior as well. The graph should show you the similar behavior. So in the analysis part, there's one population distribution of mother cells. So you can see that this is actually showing you the damage on the x-axis, and on the y-axis, this is the proportion of the population. So for all the A equals to 0, 0.25, 0.5, 0.75, and 1, these are the 5 colors that you can see in each bar section. So what's happening is that mother cell actually has damage at least 120 or above, because before that they are daughters. That's why we cannot see anything before that. And when they have damage around 420 or 479 until 540, they are actually dead. They cannot produce any more daughters.
I have another question. So you compute the damage for each cell? I mean,
yes.
Practically.
Yes.
You do like a statistic, or you take each cell and how many cells you have?
So this is all the computational work. This is not the experimental. In the experimental side, actually you have very much limitations. You can go to the colony size, but that will not be very high. And you have to individually calculate the length of all the damaged portion of the cells. So there are some softwares available right now, but still, in most of the places I've seen, when I was reading the articles and everything, I've seen that people have done manually because of the funding and all that stuff. These are the barriers.
So here you assume what is the damage, yeah?
Yeah, I'm assuming that this is the behavior that is already have seen in the experimental setup, and based on that behavior, how the results are shown. So here I was getting like 20,000-30,000 cells when a cell is dividing and producing more daughters, and those daughters were dividing and producing daughters, so that whole pedigree tree were like 20,000, and I used MATLAB. So my colleague who was using C++, he actually went until 80,000 easily. So it's advantage to use C language, C++, I think, in that case. So here the formula that I'm writing is pretty much the number of daughter cells between A to B and the total number of daughter cells that we are getting, and then you can normalize the population. I think the formulas are like interchanged because there should be the daughter and it is mother here. So this formula should be in the previous slide and this formula should be in the next slide. So in the daughter cells, you can see that all daughter cells have damage in the first until 120 or until like a little bit in 180. Most of the cells are becoming mother when they have damage until 120 to 180. In the total population, we observed that the damage is mostly below 240, and then after the damage is decreasing. And you can see for the different A's that for A equals to 1, the damage is mostly between 0 to 59. It means that the cell is selfless behavior showing, and it has all the damage right in the beginning. The reason is simply because cell is unable to produce more daughters. So it is producing all the healthy daughters, and healthy daughters are going, when they are becoming mother, they actually start their damage from 0. So that's why we can see more damage in the 0 to 59 than the first one. So here is the cost function. Now we have the population, we have the damage, and these were the two things that were required. Maximum population and minimize we wanted to minimize the damage and maximize the population. So what we can do is that we can normalize population and we can normalize the damage, and we can add them here to see that where they are going to lie. In this figure, the division strategy is the dash lines in blue color, and distance strategy is the black line. So we can see like this is not a stochastic modeling. This is totally until now we are doing deterministic work. So why this behavior is coming? Because we are using some kind of I can say discrete element modeling, or because there are each cell we are taking the behavior and we are counting them. So if cell is not divided, it will show some little bit of jumps at each point. Yeah.
With the previous slide, how do you know when to stop that simulation? Because does the distribution change over time?
This one?
Yes.
How to know when I'm going to stop the simulation?
Yes.
Okay, so like there is no definite way to stop the simulation because cells are dividing and dividing and you are getting all these things. But the only thing you can do is you can set your own criteria that, okay, when I get 20,000 cells, just stop it. There are some other ways as well that you have some arbitrary unit for the time, and you can say that until this time, just stop it after that, don't go down. I was using the later one, the time one. So I found the cost function here, and for different times t equals to 1.5, 1.75, this is the arbitrary unit for it. And it was taking so much time in MATLAB actually. I think for t equals to 1.5 it was taking a couple of days, but for the t equals to 2.25 it was taking a couple of weeks to run the simulation. You can imagine that for each point I was actually running the whole simulation, whole pedigree tree, that a cell is going to divide. There is some differential equation system that will increase the growth and the division, the damage and the healthy part, and then after it will divide with some discrete equations. It will go back and then again it will perform the same thing. So until t equals to 2.25 it was taking almost a couple of weeks to run this simulation. But I think for with C++ it can be much efficient. So there are a lot of, I call them the ditches, the ones that are coming, that are going really down. And we can see that there are a lot of local minimas there are some global minima, we can call it global minima as well, on each subplot. So now I'm coming towards the reinforcement learning algorithm. So what actually happened here is that we initialize altruism value. First of all, we choose the strategy, which strategy we want. Then initialize altruism value, find cell progeny, and find the total population and total damage, and use cost function that we defined. We made our own cost function for the. That's why I consider that we don't have any already made modeling technique. Like in case of supervised and unsupervised machine learning, we have predictive modeling techniques that we can use and just get the results. So here we have to build our own. Then after cost function, we have this some stochastic term coming that is telling us that if the direction is good, then how far you should go in the next step, and if the direction is not good, then you are going in changing the direction and in which direction you should go and how much you should go. So if this criteria is true, then we stop, otherwise we keep going on. So here is the stochastic simulation in which you can see that only the few above ones. In this one here, we have the strategy variation number, and on the y-axis we have altruism. We are saying that we are giving an altruism value and see hold the progeny, and then after we find the cost function. If the whole cost function is giving us some value, next step we will take another one. So initially we have to take one step arbitrarily in one direction. So when we will take the next step, we will compare it with the previous one, that our cost value is decreased or increased. If it is decreased, then it's good to go in the same direction. If it is increased, then we have to change it. So when we will change the directions, it will go up and down. And why it is going so much up and down, we can see on the left-hand side how much fluctuations we have in the figure. What it is showing is that the cells who are trying to follow the, trying to be, there's a term called evolutionary stable. They are trying to, from evolutionary point of view, they are trying to be optimal, and they are showing some optimal reproduction success, minimize the damage and maximize the population of the colony. They are lost. They don't know where to go actually. Even if they are finding the minimum point, they don't know that this is the minimum point. And they keep going in that direction. So when they keep going, they find some higher cost function. When they find the higher cost function, they don't know how to come back to the same step. They will jump, and they will jump somewhere else, where the cost function might be high again, and they will change the direction again. So that's why they will lose. But in some cases, in the above figure, you can see that above 0.6 altruism, they all are going to converge to 1. The reason is simply this line. You can see this is a smooth line. So if the line is smooth, they can easily converge where the minimum point is. But if the line is not smooth, as in the normal case, then they will be lost. Yeah.
So I'm trying to understand the figures on the right-hand side. The strategy variation number, from left to right, is that essentially time?
Now, strategy variation number is that. So you are taking some algorithm volume, and then you are finding the cost function. If cost function finding means that you are finding the whole population or the pedigree. There is a one single cell that has this altruism value. Now this cell is for or making your is going to divide and produce more and more daughters. Those daughters will again divide and produce a huge 20,000 cells almost together. So maybe the first mother cell had already died, first daughter cell, the first one. But still there are a lot of other cells that are in the population, in the colony. So we are calculating that whole colony population and their damage inside. So we, in the previous slide we have seen that there is a cost function. In that cost function we are summing up the damage and the total population impact. So whatever their impact is, cost function will tell us that in total it is giving us this much impact. And this impact is actually showing that which direction we are going to follow. So this is why I called it strategy variation. So they can vary according to the algorithm value. They will start varying. So if I compare it with the example, simple example, I will find very much similarities in my work and in the example that I've shown you. The first one is the imagine a kid is given with a television remote control, that is the environment. So our environment will be where the cell we are going to grow. The second thing is first the agent will observe and construct his own representation of the environment. So our agent is cell, and cell has to see how it is growing and how it is producing daughters. And then this is the state. Then his curiosity will take certain action to press keys on the remote control. That is the action. What it will do is that it will set the algorithm value accordingly and keep moving and observe how would the TV respond. Next time, it will get the cost function again next state. Find the population and by growing and dividing. So if the TV is not responding, he will dislike it. He will change the strategy and will take less action that will lead to such a response, and vice versa. He will repeat the process until he finds a policy that is giving better response. So until now, this is the portion that it is randomly following all the strategies, and where it is going to convert, it will be called as, this is its optimal reproduction success, and where it is minimizing the damage and maximizing the population. And yeah.
Why is there a difference between first draft and
First draft and second draft.
yeah.
So these are the two strategies that we followed. Actually, I should have written this thing, that the first graph is telling us about the black line here. It's corresponding with the black line there. That is actually the distance strategy. And the second graph is the beginning strategy. Yeah. Sorry, I should have written it somewhere.
So that just means that there was no convergence in the second graph, in the graph at the bottom? Or?
Yeah, there is some conversion coming here, right? You can see that right after some time they are converging as well to the side. Because the reason is that right at the end you can see that they have those cells that are coming, they are becoming more altered, like they are more selfless. They are unable to go back because there is high cost functions involved, and they just come back. The reason the results are like a bit weird at the ends, because whatever value we are giving, we are saying that don't go beyond 1. Whenever you are reaching above 1, just consider it 1. So that's why at the end, normally we have such weird behaviors, and that's why they are converging. Otherwise, if it is not 1, they might have gone somewhere else.
And color coding is for different solutions.
Which one?
CIC with like a family of curves.
Yeah,
Each of them is
yeah. Yeah, these are for each different simulations. So it was like time measurement process.
Sorry,
Yeah.
my final question is, I see that the black curve reached a plateau at 1, but the simulation is still going. Right? Why that? So the cost function
Yeah.
reached a stable value.
So on the left-hand side, the figure is actually whatever is for the cost function. So whatever we are doing until that point is deterministic. We are setting up the table for the reinforcement machine learning. For the right-hand side, actually, we are using that all thing and using our stochastic modeling approach to actually change the strategy. So these curves will keep going in the same way. If I don't stop them using my criteria that I defined in this equation. So it is just saying that if you find 5 or 6 like the steps together in which the whole sum is less than epsilon, some small value, then it means that strategy is not varying a lot. Strategy is keeping at the same place. So I'm just stopping it there. Otherwise it will keep on. So these are the only ways. I mean, you can have some different way as well. You might convert somewhere, really convert somewhere, that you don't have to do like this. There are a lot of problems in agent-based modeling, and normally in the biological sciences as well, where they think that things should converge to one value, and strategy will be like the optimum, global optimum. So yeah, that's it. That's the conclusion. And we have seen for the first one, I'm talking about the problem. Each strategy has its own minimum for cost function. The model might not be able to reach the minimum point of the cost function. As we have seen that it never converted to the minimum of the cost function. It just lost somewhere else in the other evolutionary digits that I call it. Reinforcement machine learning depends on the mathematical formulation of the underlying physical system, so that's very important, whatever you are building as a deterministic part. If this is not actually following your underlying physical system, then it means that there will be fault. Then you can do whatever with the stochastic modeling or the machine learning part. It will never converge, it will not give you good results. So you have to focus on one thing, that whatever the mathematical portion is, when you are modeling the problem, it should show the physical system. It should behave like the physical system. Yeah, that's it. Thanks a lot.
I have a few questions. So in real life, the real yeast cell, how it behaves, optimally, or it depends by the environment?
So as I've shown you that one statement, that was the key statement actually. In that sense. From evolution standpoint, these cells are tuned for optimal reproduction success and not for long-term survival. So there are thousands of yeast strains, yeast types. They all have their own retention mechanisms. Maybe they have small differences, but they have some differences. Or maybe they don't have differences in the retention mechanism, they have differences in some other things. That's why they are different from the other yeast. They are following this statement, optimal reproduction success. But in what sense they are, that's what my work was, that they are not following optimal reproduction success in a global form. They are actually stuck at some local phenomena where they are still lying and they are trying to find the global minima, but maybe they will never reach that global minima. Even if they reach that global minima, they don't know that this is global minima.
And another question, do you know any natural processes or something similar that you can apply this?
I think there are a lot of problems that just come in my mind, and I feel like these are very similar to this, and they just wash out at the same moment. So it all depends. When the problem you see, then you can understand that which problem, which type of machine learning or the deterministic model you need to set up to approach such problems.
Because I think this is a very fundamental question. Yeah?
Yeah.
I mean, you can extrapolate this to how the social network will behave or how the society.
Yeah.
If the society evolves for self-destruction or for self-preservation?
Yeah, I mean, like these all things are actually a lot of researchers, I know that they are working on these things as well, on the social norms and social learning factors. And they are also on the theoretical side, because you cannot tell anybody what is the social norm of this society unless or until you really define it in your own terms, that these are my terms of social norms. No, this society is giving me this behavior, even if maybe not. You are just taking the sample out of like millions of It all depends. If you are asking me some survey right now, maybe I will give you some different remarks. But in the morning, my attitude is different. So it all depends upon our behaviors and everything. So we cannot find one single phrase that, okay, this is the social norm of this whole society, or this is the social learning factor we need to build up the society. That's why these reinforcement learning models are very famous right now in the research community. Especially I've worked on this side, in the biological side and in the ecology side as well, with their community learning model. So I think it all depends on the problem, then you can set up.
So do human cells have what this law of optimal reproduction success?
No. So that's the thing. That's good that in the yeast cell that they are retaining damage, and with the passage of time they lose this retention. In human beings, it is fortunately not the case. We are able to retain the damage in the next generation as well, but the problem comes that we still transfer some diseases to the next generation, and these are genetic diseases, right? These are not based on the damage. These are based on the genetic modifications in our body. Yeah.
So my question might be two-headed, so I'm just going back to two different versions.
Sure.
One is, in a lab environment, is there a way to enforce this altruism level? And the other version of it is how to quantify altruism in a society.
Yeah, I mean, like, these cannot be counted. These are uncountable things. Like, how can you tell somebody that you are more altruist and you are more selfless than the other if you don't have any predefined criteria in your mind or something? So in the lab environment, what you can see is that how the yeast cells are behaving, what is their damage retention mechanisms. In their first few daughters, how much they retain, and with the next daughters, how much they are going to give them the damage. So based on this thing, you can define your strategies, and you can formulate the force functions. Saying that how much altruism they have, it might be according to your deterministic model, that how you are defining the altruism.
I think in a lab it's harder to control a lot of the other conditions like providing food and starvation issues or overcrowding issues, things like that.
Yeah.
Whereas with the computer simulation model, you can ignore all that.
Yeah, there are a lot of things, but what we do is that we always think that there is enough food available for them, because our results are not based on some sort of decades. They are based on some sort of 1, 2 days or 3 days work. A yeast cell can divide within some, I don't know how much time. I think it takes a couple of hours. So I feel like in these works normally we make models not for long term but for short terms. If we are really trying to follow the experimental behavior. But if we are trying to say something more theoretical, then we try to take it for a long period of time as well. But our conditions are same. That we are saying that we are providing you enough food and everything.
I guess that would complicate the model quite a bit to
Yeah.
introduce all these other factors. Things that need to thought of.
So the good thing about this reinforcement machine learning model and thing is that there are some predefined things that if even I put those values inside, of course from the experimental setup I need to validate them. That my model is actually behaving in the same way as in the experimental labs. If it is not behaving in that way, then it might show you some weird results that are not true. So whatever we are doing until deterministic modeling, our setup should be similar or some sort of showing some behavior in the realistic environment. I hope I answered you. Yeah.
So I guess these population of
like populations of yeast with homogeneous populations and strategies they choose? Is that right?
So, from the evolutionary point of view, we always say that these are the strategies they are using. Actually, they are doing nothing. They are just, they are designed in this way that they have to follow this routine. So, what was your
Is the whole population using the same strategy?
they will divert from the whatever the strategy is. But here I'm ignoring that thing. That I'm saying that okay, one strategy is defined, then it will follow by the whole program.
Do you think that it did include some, it took away some of these assumptions that there being like food or something kind of affect each other?
Yeah.
Like a homogeneous population.
Yeah. So this will of course, but it will be difficult to find the conclusions. Means here I am saying that okay, I know that what behavior is, but if I am allowing it to deviate from the real altruist value a little bit, then it will be difficult to say that okay, for this altruism value, this is my result. They are deviating, so I can't say that.
Thank you very much.
Thank you.